Okay, so today we will discuss the last topic in this course, which is operational amplifiers. We don't have enough time to cover the rest, while there are some other things that I hope to include here, which is like including the signals and sensors part of analog to digital converter, or part of something related to digital logic like binary, decimal, these numbers. Unfortunately, we don't have enough time. So operational amplifiers will be our last topic. So what does operational amplifiers mean? What's the importance of this? Operational amplifiers are basically some electronic circuits, and these electronic circuits can be used to amplify any signal. So before going to the operational amplifiers, I'm going to go a little bit discuss about the signals, electrical signals in general. The electrical signals can be either power signal or can be data signal. What does power mean? What does data mean? Power signal, those are the signals that we can use them to power up the devices. So power up the devices like turn on the lights, the signals that use in batteries, so something that to power up the electronic device, your cell phone, power up your cell phone, power up your any device like the refrigerator, air conditioner, etc. So which is what we discuss, the most likely we discuss in this course some applications related to the power, like transformers, power lines, power electronics, all of these applications, power factor corrections, all of them are related to something we call it power, which is the energy or the electricity that we have to do some energy. While there are other part of signals that we can use, they are not considered as power signals, like the communications, the wireless communications. All of them are the satellites, the internet signals. All of these are called data signals, which means these signals have a meaning, have some information. While the power signal, I expect to see what's the signal from the power, which is, I know 120 volts, cosine wave, 60 hertz. We know the power signal. We know what the waveform will be. So we are using this just how much energy it will consume, how much currents, because the voltage is constant. P equals V times I. V is constant. The more power you need, the more current you will consume. That's for the power. For the data, you cannot predict what's the data. So which is based on the internet, or for example, the radio. You can say radio AM, FM, the satellite signals, 4G, 5G, signals, all of these communications, wireless, the Wi-Fi signal, you can find it everywhere. Those signals have a low power. Those signals will be used only for communications, or for this data will the signals have a meaning. So this will not be powering the devices. So you cannot use the signal from the, for example, 4G, 5G to power up a light bulb, or to power up like a car or something like that. Because all of this, the meaning of them, it's what's inside or the contents of it. You cannot use the radio signal to power up a device. That's why when you are using your radio, you put a battery. When you are using your cell phone, you put a battery, right? You are not using the wave energy that we have. So when you have a detection, like signals detection, you will see here we are filled with many signals, many wireless signals. Again, like a Wi-Fi, your cell phone, GPS, etc. Anything. We have many things, but this cannot be used to power up anything. How can I use it? Or what should I use them? We will use them as data. As an example for the data signal, now I'm talking, then you can hear me through the speaker. So I'm talking here. The microphone is converting my voice from a voice to be an electrical signal. That electrical signal have a meaning. Then my voice will be transmitted through here. There's a wireless and there's an antenna. It will be transmitted wireless to the speakers, the receiver of the speakers. So the receiver will receive that signal and convert my voice or amplify my voice. Then it will go to the speakers. Then you can hear it. So most likely the microphone will convert my voice into millivolt scales. It can be, I'm not sure, like 100 millivolts, 200 millivolts, in a specific range. The speakers can handle, or in order to hear my voice through the speakers, you need to have it 15 volts, 10 volts, something like that. So we can see that the speakers can handle 10 volts, my voice through the microphone in millivolts. Okay, so how can you hear me? Using the amplifier. So there is an amplifier will boost the signal from millivolts scale to be 10 volts scale or 15 volts, whatever. So then you can, then my voice or will be converted, the electrical signal will be converted to 15 volts scale as an example. Then it will go to the speaker. And you know, I'm not sure if you know the speaker, which is it will vibrate, the number of vibration will produce the moving. So that's how you can hear me. Then without the amplifier, this will not be happening. The other thing, I cannot use my voice to power up the devices, to power up the speakers, or I cannot use my voice to power up the transmitter. So that's why there is a batteries in the microphone, in the transmitter, and there is a batteries to power up the speakers. So I cannot, again, use them. So the most important thing is the information, which is my voice. I want my voice to hear it clear through the speakers. Then we need to amplify my voice. So the question is, how can I amplify it? Using the amplifiers. So you can say, I need to boost up the signals, or step up the signal from millivolts to, for example, 10 volts, 15 volts, which is we need to step up the voltages. How can I step up the voltage? What do you think? Any thoughts? Yes, that's a good question. That's a good answer. So is it transformers? Okay, we studied the transformers that we can boost up the signal. Yes, step up the signal. Okay, but the question is, do you think the transformer is a good idea? So the transformer is good approach when we have the signal on AC and that signal as sine or cosine wave. While my voice is not guaranteed, it can be changing. It can be sometimes speaking more loudly, sometimes speaking calm, so it will not be uniform. And we cannot predict the waveform. So we cannot say, okay, the transformer is not good, is not actually a good idea because the transformer is suitable when we know what's the waveform, and it is suitable when it is only in AC. If it is in DC, there will be a problem, and it's suitable when we know the waveform. Or in other words, suitable in power area. While here, the transformer is not a good idea. Okay. Is there any other devices? Recall the power electronics overview lecture. So there was AC to AC, DC to DC converter using the power electronics devices. So the power electronics devices is not good to approach as well. Why it's not good? The problem of the power electronics, or I know my targets, I need to satisfy my targets. So the power electronics, basically, I have the inputs, I have a desired outputs, so I'm designing a circuits to get the desired outputs. While in this situation, I don't know the outputs. I mean, I can say the output range will be between this, yes. But I don't know, you cannot predict what I'm going to talk in the free. Or someone else can use the microphone, can talk different chords, different things. So we cannot predict this. Therefore, it will not work out well as well. Okay, what should I do? There is an electronic circuit called operational amplifiers, or the amplifiers. Maybe you heard about the amplifiers a lot. If you make a party and you're using DJ or whatever, then you need to use the amplifier so you can control the signal, or you can use the mic so you can use control the voice or the volume, whatever. Then the amplifier is basically actually an electronic circuit, and that electronic circuit needs, of course, needs a signal like power up, needs some external power supply. It's an electronic circuit that you can be used to power up or to amplify the signal. So that's our topic, which is operational amplifiers to amplify the circuit. It can be used not only in the microphone applications, it can be used in some medical devices. For example, when there's a medical devices, instrumentation, like measuring, for example, the heart rate, measuring whatever, we see like different type of signals, then these signals basically in millivolts. We need to keep the data. The data is important. And we need to let this measurable, so we can measure this to the electronics, to the monitors, whatever. So we need to amplify these signals. It can be used also in medical devices. And it can be used in control systems when you have a measurements, like a thermometer measurements, the thermometer most likely converting the temperature into a voltage signals in millivolts. Then we can use this to go to the microcontrollers, but the microcontrollers most likely can handle it. For example, they're doing it between 0 to 5 volts. We need to amplify this signal into this step. Some devices like this. Some microcontrollers can handle millivolts, whatever, depending on the microcontrollers. So you need to have a feedback. You know, in the control system, I'm not sure if you took the control system class, but when you take it, you will hear about, or you will learn about something called the closed loop control. The closed loop control, this requires a feedback from the sensors. So the sensors measurements, sometimes it can be very low. You need to amplify these sensors measurements so the microcontrollers or the controller that you have can know how much signals that you have, or can understand the signal. So you need to amplify it so it can be measurable. So it can, the microcontrollers can measure, can be readable, make this information readable. Okay? So the microcontrollers, again, there are different ways, the operational amplifiers, different ways. So there are two models. There's the ideal model, non-ideal model. In real life, it's a non-ideal model. But as a shortcut to make it simplify as simple as possible, we will go through the ideal modeling. So this course here, we will discuss the ideal model. Okay. So this is how the op-amp looks like this triangular shape. Keep in mind, this is totally different than the diodes. The diodes, it's small rectangle, triangular shape, and with this. But this is totally different, and this is bigger than the symbol of the diode. And there are five different things. We have V outs, this is the terminal, two inputs, V plus, V minus. Then we have VDD, VSS. VDD and VSS, this is the positive, this is the negative, which is the biasing, or in other words, we call it the power rails. Because any electronic device, you need to have a positive and negative terminals. You can imagine that when you have your cell phone, it's an electronic device. There is a battery on it. The battery has a positive part and negative parts. Or when you connect to the power outlets, there is a live and a neutral. So you need to have positive and negative. Then we have here, any electronic device will be positive and negative. So VDD and VSS, those are called the power rails. Then the open loop model, this is the open loop model. Then it will be as V outs equal gain, V plus minus V minus. So the gain can be gains called open loop gain, can be 10,000 up to 1 million or more. This is very high gain. Again, VSS and VDD, those are the power rails. The output voltage must be bounded between the power rails, VSS and VDD. This is a must. And this is something important. Because I cannot produce energy from nothing. The energy will be transferred from one shape to another. So when I have the power supplied between 0, for example, to 100, I cannot generate an output higher than 100 or lower than 0. You can imagine that I'm here in this room between the floor and the ceiling. So I'm bounded between this. I cannot go higher than the floor or lower than the floor or higher than the ceiling. So I must be bounded between the boundaries that I have. So it's bounded between VSS and VDD. Okay, so how does the practical model look like? Like this. This is not included, but this is just a demonstration to show you how it's complicated it is. So this is the model, and this is how it looks like inside the triangular shape. So you can see something like the blue rectangular boxes. The blue rectangular boxes are actually resistors. But some schematic diagrams, they make them as rectangular. Then you can see other thing which is with arrow and 3 legs, or this is called transistor. So this circuit is actually a combination of transistors. And you see capacitors, resistors. Then that's one model of the operational amplifiers. Then you can see it has, I think, 5 terminals. And these 5 terminals with a combination. Then as a shortcut, we will not discuss this circuit. We will consider the equivalent model for it, which is that box, or that triangular box. Okay? Some textbook, they modeled these transistors and resistors to be as this equivalent circuit, like a resistor and resistor with independent voltage source. This voltage source comes as rectangular. We haven't discussed this, which is called it's called dependence voltage source. This is voltage dependent voltage source. This is more advanced topic. So again, also this module will not be included to you. But in most of electrical engineering courses, they use this model in their analysis. But for us, we will consider the ideal model. So don't worry about this one as well. Okay, we will consider that one, this one here. That's what we will consider. So in order to make it simplify as an ideal model, again, this is for the ideal model assumption, we will assume the closed loop gain as infinity. This yields the positive voltage equal to the negative parts. Okay? The positive and the negative are not physically connected, but they will be the same. Okay? Then the currents, no current will flow into the op amps. So no current will flow in the op amps. So I plus will equal to I minus. These two rules that are important, and we will apply it everywhere. Okay? Now we should be ready or good to go to the application. So again, these two rules that we will use in our analysis. The first application number 1, is called buffer amplifier. So the buffer amplifier, basically, this is how the circuit looks like. You need to either memorize this circuit, or you can write this in your note sheets. So in the quiz, I think it will be open notes, as I told you, on Wednesday. So that's fine. But for the final exam, you need to keep in mind to either memorize this circuit as a buffer, or you can look at this circuit or write it in your note sheets. Okay. How we can treat this? So V out equal closed loop gain times Vn. Since open loop gain. So open loop gain here will be infinity. This is I plus equal to V plus equal to V minus. So anyway, the rules that we have, number 1, V plus equals to V minus. Rule number 2, I plus equal to I minus, which is equal to 0. Okay. How can I solve this circuit? My target is to find V outs and IR. Okay. This one, how can I do it? You can label the nodes. This is V plus. This is V minus. Therefore, they are the same node. This is a node. Or let me change the node in different colors. This is a node, the green node. And V minus is the same as V plus. Then this is the green node. Then all of this green node. This yields what? By looking at this. Then this yields V inputs equals V plus equals V minus, which is equal to V outs. As a result, V outs equal to Vn. Right? This is V out is the same node at Vn. So V out equals to Vn. So we can say whenever we have buffer amplifier, V out equal to Vn. So in summary, I would say V outs equals AV. AV is called closed loop gain times Vn. Then in buffer, closed loop gain AV equal to 1. Okay? And when you do your analysis, don't say alone just V out equal to Vn. Don't forget the other thing, which is checking saturation. Check saturation. So basically, you need to check, is Vn bounded between VSS and VDD? If yes, then V out will be the same thing that you found it. If Vn lower than VSS, then, I'm sorry, here is V out. If V out lower than VSS, then V out will be VSS. If I need to go the lowest points, since I'm bounded in this room, the lowest point is the floor. So I cannot go lower than the floor. If V out larger than VDD in our analysis, then V out will be equal to VDD. If I need to go the highest point, which is the ceiling. Even if my target is higher than the ceiling, I cannot go beyond that point. So I can plot the graph of the V out. So it will be like this linear relationship, then it will be, it cannot go higher than VDD or lower than VSS. Okay? So with this situation, it is called saturation. Okay? Saturation means it is out of the limits. My targets is, for example, let's assume my bound between 0 to 10 volts. My target to reach 15. But since my limits said, okay, that's the maximum thing that I can have is 10, then I will give the output 10. Then there should be an indication, like a light bulb, it's called saturated. Then we can understand that there is something wrong, which is the output is not like what's supposed to be. Okay? You can imagine the saturation like you have $10 and I said, okay, I need $20 from you. So you said, I didn't have the maximum that I have, which is $10. So I'll say, okay, I will take the 10. Then I owe you 10. I still owe you another 10. Since I still owe you, this is a red flag, or this is means there's a saturation, which is I didn't take what I want. Okay? So we need to keep this in mind. Okay, for this application, the most important thing, V out equal AV, which is closed loop gain times Vn. Buffer, closed loop gain will be 1. Then don't forget to check saturation. Does V out is bounded between VSS and VDD? If yes, that's fine. If no, just it will be saturated. Okay. How about to calculate IR? To calculate IR, it is V out over R. And we know how to calculate V out. This is I sub R. So someone can say, what's the point of this application since outputs equal to the inputs? It seems useless, right? Okay. What's the benefits of it? So the benefits of it is to isolate the output from the inputs. Okay. How? The point is, in some applications, especially in medical devices, we need to isolate the input and the output, so we don't want to consume the signals or to consume the power of the signals from the data. We want to consume the power from VSS and VDD, which is from the power, from the, for example, the plug or from the battery. So the point is, I don't want to consume the energy of the data, which is using the data signal to power up the electronics devices. So with this application, we can guarantee if we need power to supply the load, here is the load. If the load needs power to be supplied, the load will take it from VDD and VSS. So the energy or the current or the power that will be consumed in the resistor which is the load, or the, for example, the monitor of the medical device, whatever we have, it will be consumed by VSS and VDD, while the inputs will be the same as the output. Then I can see it at the monitor. Okay? That's the key of using this. Isolating the inputs from the outputs, so I don't want to consume energy from the inputs. Okay. So here they say like the application. This is used in microphones, medical electrodes, radio receiver as well. Where is the data? Again, very important, and we need to use this data. Don't use this data to power up the devices. We need to isolate this data. Okay? Second application, non-inverting amplifier. Non-inverting, keep in mind, inputs enters the positive. Okay? In buffer, inputs enters the positive. So it's very similar to the buffer. What's the difference between it and the buffer? In the buffer, there is no resistors in the feedback. You look at the feedback, this is the feedback, no resistors. Here, there are two resistors. That's the difference. If R2 and R1 are both zeros, then this yields a buffer circuit. Or if R2 actually is 0 and R1 is open circuit, this yields a buffer circuit. Okay? Then this is called non-inverting. What's the point of called non-inverting? It's in purpose because non-inverting, because the input enters the positive. Okay? If input enters the negative, it will be called inverting amplifier. Then, how is the formula will be? It will be as the V outs equals closed loop gain times Vin. Then, the closed loop gain here will be 1 plus R2 over R1. So R2 is the feedback resistor. Here is R2. R1 is the feed forward resistor. Okay? Feedback over feed forward. So 1 plus R2 over R1, this is the closed loop gain. After you calculate the closed loop gain and calculate everything, don't forget to check saturation. Here's the procedure. It's very important. Check saturation. Basically, V out must be bounded between VSS and VDD. This is very important step. Okay? Does this make sense? So this is the second application. Now let's move to the third one. Let me give you some time to write. Then we'll move to the third one. Okay. Third application, I will go back to the example later. Let me go to the third part, then we will discuss the example. Third application, inverting amplifiers. Inverting amplifiers, you can notice since it is inverting, the input enters the negative. That's the difference. Non-inverting, input enters positive. Inverting, input enters the negative. Okay? Then, since the input enters the negative, how it will look like, it will be here V outs equals to the closed loop gain times Vn. Then the closed loop gain here will be negative R2 over R1, which is the negative feedback over forward resistor. R2 is feedback, R1 is forward. Okay? So negative R2 over R1. Then don't forget to check saturation, which is V outs must be bounded between VSS and VDD. Okay? So how can I distinguish? Is this one inverting, non-inverting, buffer? Buffer, no resistors at all. Inverting, the input enters the negative, then this yields to a negative output. The non-inverting input enters the positive. Okay, does this make sense? Okay. Now let me draw the, or let me just write a summary, quick summary. the summary, V out equal closed loop gain times Vn. Okay, what's the closed loop gain? Closed loop gain can be different cases. If you have a buffer, closed loop gain equal 1. If non-inverting, closed loop gain equals 1 plus R2 over R1. If it is inverting, closed loop gain equal to negative R2 over R1. Then, after that, what we will do, which is basically check saturation. Then, which is basically V outs will be bounded between VSS and VDD. And then after that, if you need to calculate the currents, then I, for example, load will be V out over R. That's what you need. That's the summary. Actually, if you write this summary as a note card for you in the quiz, this will be fine, in addition to chapter 9. I mean, that summarizes everything. But the point is, the key is, you need to know which, and when you look at the circuits, which type of amplifier is this one? Is this one buffer? Is this one op-amp or not op-amp? So the first step, identify the circuits. The second step, identify which one is the feedback, which one is the feed forward, which one is R2, which one is R1. After that, apply V out equal, or find the closed loop gain, which is AV. Then after that, find V output, check saturation, then IR. So I can say the steps, identify the circuit, then find closed loop gain, then find V outs, then check saturation, then number 5, which is find I, if needed. Then if you need to calculate the power, will be I squared times R, or V times I, or V squared over R. So keep in mind here, most likely we will go in DC circuit. So we will not go in AC on op-amps, okay? So we will try to make it simple. So we will not go to the complex power or the other things. So these are the procedures. I encourage you to write them. Then that's how we will do it when we solve the. We will go through now through a couple of examples. That's what we will discuss. Let me give you the time to write, and I will go to these examples. Okay. Let's go to this example. In this circuit, we need to calculate, in summary, when V input equal 1, when V input equal 3. So we have two cases. When V inputs equal 1 volts, and the other one, when V inputs equal 3 volts. So the first one is case A, the second one case B. We need to do our analysis. So the first step, according to the procedure that I already wrote here, identify the circuits. Is this one buffer? No, there are resistors, 4K and 1K. Is this one inverting? No. Look at the inputs, enters the positive, therefore it is non-inverting, okay? Again, why it's non-inverting? The input enters the positive. So it is non-inverting. So recall, in non-inverting, the second procedure, which is closed loop gain equal 1 plus R2 over R1. Which one is R2, which one is R1? Here it's not written. You need to know it. Look at the feedback resistor. So this is R2. Feed forward, which is R1. Here is R1. So since we said like we need to find it, then we have two cases. or no, sorry, we still have one case, which is R2 over R1. Let's substitute to find the closed loop gain, which will be 1 plus R2, 4 kilo, over R1, which is 1 kilo. Kilo and kilo cancel each other, 4 over 1, 4. 1 plus 4 equal to 5. That's the closed loop gain. Then, the next step, according to our procedure, which is we need to find Vouts. Vouts equals closed loop gain times Vn. Closed loop gain here equal to 5. Therefore, Vout will be 5 times Vn, right? Now, what's Vn? We have two cases, A and B. Let's do case A here first. Case A, when Vn equals 1 volt. So this yields Vouts to be 5 times 1. Then it will be 5 volts. Okay, what's next? Check saturation. Look at the op-amp, it is bounded between -10 and 10. So, the question is, does Vouts bounded between -10 to 10, which is basically Vout here equal to 5. Is 5 between -10 to 10? Yes. So, that's fine. It's not saturated. So what we will say, Vouts will be the same thing that we got, which is 5 volts. Then the last step to calculate I will be Vouts over R. So Vout here is 5 over R, 500. 5 over 500, we'll make it 1 over 100, then it will be 10 milliampere. 10 milliampere. If you need to calculate the power, it is I squared times R. Then you can do it if you need, which is 10 times 10 power -3 square times 500. Then you can calculate it. I don't know actually the answer, but if you need to do it, you can do it. That's parts number A, then done. Again, you need just to read the question carefully to see, do we need to calculate the power or not? Do we need to calculate the current or not? Here, just I make it in case if we need to calculate the power. Part B, when Vn equals to 3 volts. Okay, how can I solve the question? Basically, Vouts equals closed loop gain 5 times Vn 3. 5 times 3, 15 volts. Now check saturation. Now, is 15 bounded between -10 to 10? No. So therefore, it is saturated. So the output will be what? How much? 10. You can imagine like I need $15 from you, but you got 10. So I will take 10. Okay? And saturate it. So that's Vouts. So what will happen to I? Will be Vouts over R, which is 10 over 500, so the answer will be 20 milliamperes. Then if you need to calculate the power, will be I squared times R, then 20 times 10 power -3 squared times 500. Keep in mind, saturation is something undesired, something we don't want this to happen. That's why we need to check it to make sure, are we safe? Are we in the safe level? So if it is saturated, it will give you, or basically in the hardware, it will give you like some warning lights. Like if there is an LED light, well, small LED, it will be turned on as red, which means it's saturated. There's something wrong. So this is very important, especially also when you have a medical devices, if there's saturation, so you can understand there's false information or there's some missing information. There's something wrong with the reading. Don't consider this reading. Okay? That's why we need to check saturation every time. Make sure, are we on the good level? Okay, does this make sense? So this is an example of op-amp, and that's simple. Just make sure to identify the circuit. You need to know how to apply the procedure, then that's it. This is actually one of the simplest topics for this course. Let's go to another example. Like this one. Here we have case A when input equal 2 volts, case B when input equal 10 volts. Look at these circuits. The first thing, we need to identify the circuits. What's this circuit? Is it buffer? No, inverting, non-inverting. Inverting. How did I judge? Look at the input, enters the negative. The second thing, where is R1, where is R2? Where's the feedback, where's the forward? Here is R1, basically we know it. Okay, now how about R2? We have 10 kilo, 15 kilo. Which one of them is R2? What do you think? Both of them. So which, I mean, an R2, I need to have a one value resistor. What do you think R2 will be?
1.5.
The parallel, correct. Basically, it will be their equivalent. So here in this example, they are parallel. Maybe in some other examples, it can be a multiple of series parallel resistors. So basically, it will be the R equivalents of here. R equivalents of this circuit. This is R2. So the equivalent here is parallel. 15 parallel with 10. This will be 6 kilo ohms. So R2 will be 6 kilo ohms. Then in this circuit, we already identified it as inverting. Then we can say closed loop gain will be negative R2 over R1, which is negative R2 here 6 kilo over R1 2 kilo. Kilo and kilo cancel each other, 6 over 2, 3, so it will be negative 3. Don't forget, it must be negative because it's inverting. And it's entering the negative sign, then it must be negative. So the next step, to calculate V out. V out will be closed loop gain times Vn. Keep in mind, it will be negative 3 Vn. That's why it's called inverting. If the input is negative, the output will be positive. If the output is positive, the input will be negative, which is will be inverting the sign. Okay, that's the name of it. It's inverting amplifier. Then, step number or case A, when Vn equals 2 volts. Case B, when Vn equals to 10 volts. Okay, let's do with the first one, when Vn equals to 2 volts. So V out will be negative 3 times 2, which will make it negative 6 volts. Now, check saturation. Does negative 6 bounded between here, it's between negative 20 to 20. Is it between negative 20 to 20? Yes, it is. So V out will be the same, negative 6 volts. No problem with that. So how to calculate the currents? I, R, will be V out over R. V out here is negative 6, R, which is 2 kilo. Then this will make it negative 3 milliamperes. That's step number 1. Again, how did I bring negative 2 kilo ohms? It's 1 kilo ohm. It's 1 kilo. 1 kilo, that will make it 6 milli. It is given here, 1 kilo ohm. Okay? Step number 2, when Vn equal 10 volts. V out will be negative 3 times 10, then this yields negative 30 volts. Check saturation. Is it bounded between, is negative 30 between negative 20 and 20? No, it is saturated. So don't forget to write the word saturated. It is very important. It is very crucial to write it in your answer. Since it's saturated, this yields V out to be, what do you think the output will be? Negative. Don't forget the negative 20. Negative 20 volts. So in order to calculate the currents, I, R, will be V out over R, which is negative 20 over 1 kilo. So the answer will be negative 20 milliampere. Okay? Does this make sense? If you need to calculate the power, just I squared times R. You know how to do it. Or V squared over R, or whatever, or V times I. You know both V, you know I, you know R. So whatever more formula convenient for you, you can do it. Any question? So you see, it is simple circuits. There are some other types of op-amps. We have something called summer op-amp. This is number 4. Summing op-amp, it is actually a special case or more wide case or special of inverting.
So basically, remove R2, V2, remove V3, we have only this one. Then the input enters a positive, therefore it is inverting, right? Now the concern is, or the point is, we add multiple inputs. How can we treat this? So then since we have multiple inputs, so we can say V out equals to sum of closed loop gains times Vi, depending on the number of inputs. So we can say it is AV1 times V1 plus AV2 times V2 plus AV3 times V3, etc. Okay, how can I find AV1, AV2, AV3? You can say AVI will be negative RF over RI, which is here is feedback over this one, or this one, or this one. So as a result, we can say AV1 will be negative RF over V1. AV2 will be negative RF over V2. AV3 will be negative RF over, I'm sorry, not AV, over R. Over R1, over R2, here is over R3. Okay? Does this make sense? So the point of this one, summing amplifier, or we are grouping all of them. Why it's called summing, since all of them are negative? You can make a negative, put them in a bracket. So you can look at here, this example. We put a negative as in the brackets. This yields all of the inputs will be summed. And it is called weighted sum. So we can make the ratio between RF over R3. If all of them are equal to each other, this will lead to be V1 plus V2, V3. Or if you need to change the weights, you can make, for example, 2V1 plus 5V2 plus 3V3. You can change the ratios between the resistors. Then you can adjust it as much as you want. Okay? So this is summing amplifier, op-amp. This is side number 4. Then we can use it in our analysis as well. Okay, keep in mind you need to know how to make this, apply this formula, then everything should be good. Okay, so there is other two types. Those are not included, but for your information, which is called integrator and differentiator. So integrator, you will see there is a capacitor here. Differentiator, the capacitor will be in the forward, in the feedback or the forward. So the outputs here will be the integral of the inputs. The first one, integrator. Differentiator, the output will be the derivative. Okay, what's the point of using those? Those are not included, so don't worry about them. What's the point of making integration, derivative? Now we did integration, derivative, summing. We did also buffer, etc., and in inverting, non-inverting. Then we can actually solve differential equations using the circuit analysis, using the op-amp. So you can build any first order, second order, third order, fourth order differential equation. You can solve it using operational amplifiers, build the circuits, and get the outputs. And that's actually one of, I think, in the control systems labs. I'm not sure, maybe it's not me in here in Oman, maybe in different universities, but they used to have an experiment. Solve this differential equation, or you need to design the circuit. So you will do it in hardware. You will put the op-amps in hardware and try to connect them, design the resistors. Then you can solve the outputs to find the put inputs. So find the outputs, or you can look at it, but after building your design, look at the outputs and solve it analytically using the math. Then you can compare the math answer with your circuit answer. So this will make it more fun. So you can solve the math using the circuits. Okay, so this is the end of today's lecture.